Bismillahirrahmanirrahim. Welcome students to the week 10 lecture. This is the last topic we will cover in the chapter 16, and that is the transfer functions. Transfer function Hs is the ratio of the output response Ys to the input response Xs, assuming all the initial conditions are 0. So it is basically the ratio of the output signal to the input signal in the S domain. Ht is the impulse response function, which will be discussed later, and basically that is the inverse Laplace transform of the Hs, that is the transfer function. So Hs is the transfer function in the S domain, and Ht is its equivalent in the time domain. There are 4 types of transfer functions or gains. Number 1, Hs equal to voltage gain, and it is the ratio of output voltage to the input voltage in S domain. Number 2, if it is a current gain, the transfer function, then it is given by output current to the input current ratio. If it is an impedance, then it is the ratio of the voltage to the current in S domain. And if it is an admittance, it is the ratio of the current to the voltage. Now, we will explain the concept of the transfer function with the help of examples. Example: the output of a linear system is given, which is yt is equal to 10 e raised to the power minus t cos of 4t. So this is the output response in time domain when the input is xt, which is equal to e raised to the power minus t ut. Find the transfer function of the system and its impulse response. So hs and ht are unknown. So what we will do, we will transform yt and xt into S domain. Then we will apply the equation. Hs is basically the ratio of Ys to Xs. So we will get Hs in this format. And then we will apply the inverse Laplace transform, and using the properties of the inverse Laplace transform, we will get the impulse response h of t as given. Now the example is explained in the following slide. Solution of the previous example. So if x of t is equal to e raised to the power minus t ut and yt is equal to 10 e raised to the power minus t cos of 4t ut, then x of s, which is the Laplace transform of e raised to the power minus t, so e raised to the power minus t will have a Laplace transform 1 over s plus 1. Similarly, y of s is the Laplace transform of yt, and we are using here the frequency shift property of the Laplace transform of the cosine. So you see here we will get 10 s plus 1 because cos of 4t is multiplied by e raised to the power minus t. So that's why 10 into s plus 1 divided by s plus 1 whole square plus 4 square. Here the property of the Laplace transform is used. Now we can easily find the transfer function, which is equal to ys divided by xs. Ys is given, xs is given. Now take the division of both. So that is, you see here, 10 s plus 1 whole square divided by s plus 1 whole square plus 16. You can expand the square term. So that is the final form of the transfer function. Now we can find the impulse response, which is h of t, and for that we will write the transfer function in this format. Hs is equal to 10 minus 40 4 divided by s plus 1 whole square plus 4 whole square. So basically, in order to get the inverse Laplace transform by applying the properties of the Laplace transform, we have to write the Hs in this format. And if we can simplify this, equation, we will get the original that equation, that is 10s square plus 2s plus 1 divided by s square plus 2s plus 17. Now we can apply the properties of the Laplace transform which were given in table 15.2 in the chapter 15. So h of t will be equal to 10 delta t, because the inverse Laplace transform of 1 is delta t, minus 40 e raised to the power minus t sine 40. So the term which is 4 divided by s plus 1 whole square plus 4 square, it will have this inverse Laplace transform 4 times s sine 40. So that is the impulse response which was required. Here is another example, simple example. The transfer function of a linear system is given, which is hs 2s divided by s plus 6. Find the output signal yt due to the input 10 e raised to the power minus 3t ut. So if the input xt is 10 e raised to the power minus 3t ut, then we have to find the output signal yt and its impulse response h of t. So y of t is unknown and h of t is unknown. So let us solve it. Solution is given here. If x is the input signal is 10 e raised to the power minus 3 u of t, then the Laplace transform of xt will be equal to 10 divided by s plus 3, because 1 over s plus 3 is the Laplace transform of e raised to the power minus 3t. Now we can easily find y of s, which is the product of h of s and x of s. So h of s is given in the example, which was equal to 2s divided by s plus 3. So multiplying will give you 20s divided by s plus 3 into s plus 6. Now this can be decomposed into two components by using partial fraction. So a divided by s plus 3 plus b divided by s plus 6. Now we can find the a's and b's by using the method of partial fraction. Okay, multiplying ys by s plus 3 and then putting s is equal to minus 3 will give us a, multiplying y of s with s plus 6 and then putting s is equal to minus 6 will give us b, which is equal to 40. Putting the values of a and b in the equation, so we got it minus 20 divided by s plus 3 plus 40 divided by s plus 6. Now if we take inverse Laplace transform, so we will get minus 20 e raised to power minus 3t, and for this term we will get 40 e raised to power minus 6 of t, and multiplying all with u of t. That means this time domain equation is valid for t is greater than or equal to 0 because of the step response function. Similarly, h of s was given, which was equal to 2s divided by s plus 6. Now this equation can be simplified as 2s plus 6 minus 6, because plus 6 will cancel out minus 6, so it is the same equation. Now if we further simplify it, it will be 2 minus 12 divided by s plus 6. Now taking inverse Laplace transform, so the inverse Laplace of 2 is 2 delta function delta t minus 12 e raised to power minus 6 t ut. So that is the impulse response. Here is another example. Determine the transfer function h of s, which is equal to v naught s divided by is for the circuit given below. So the transfer function is unknown. So first of all, we have to find out v naught in terms of I naught. So for v naught, we have to find out I naught as well. And then we will get the transfer function h of s. So let us do it. This can be easily solved by using the current division rule. First of all, we will find I2, because V0 can be only found if we know I2. V0 will be equal to twice I2 by Ohm's law. So I2 can be found by the current division rule, because the current I0 is divided into two branches. So I2 is equal to the S plus 4, which is the impedance of the opposite branch, divided by the total impedance of the two branches. Okay, so one is this central branch and one is the other, the output branch. In the output branch we have a capacitance of 1 over 2s plus a series resistance of 2 ohm. So that's why by current division rule, it is the I2 is equal to S plus 4 divided by S plus 4 plus the impedance of the output branch, which is 2 plus 1 over 2s, and then multiplying with the source current, the input current, which is I0. Because I0 it is divided into I2 and I1. Similarly, we can also find I1 by current division rule. Now, putting the value of I2 by applying Ohm's law in order to find V0. So V0 is equal to twice I2. So just this equation is multiplied by 2. Now, dividing both sides of this equation, V0 equation, by I0. So we will get the transfer function. So H of S is equal to V0 divided by I0 S, and it is equal to 4S into S plus 4 divided by 2s square plus 12s plus 1, because you need, if you take the LCM of the denominator term, the LCM will be 2s. So that 2s, if goes to the it will multiply with the numerator, which is equal, that will give you 4s into s plus 4. So that is the transfer function of the circuit, and this was unknown, so this is the answer. Again, on the same pattern, we have another example for the same circuit. Find the transfer function Hs, which is equal to I1 divided by I0. Okay, so this is very simple, one step problem. We will find I1 by current rule, divider rule, and then we will find the transfer function. So by current division rule, I1 is equal to the impedance of the opposite branch, which is 2 plus 1 over 2s divided by the total impedance of the two branches. So that is S plus 4 plus 2 plus 1 over 2s multiplied by the source current, the input current, that is I0, because that current is divided into I1 and I2. Now, if we divide both sides of the I1 equation, so we will get the transfer function, which is equal to Hs equal to I1 divided by I0 is equal to 2 plus 1 over 2s divided by S plus 4 plus 2 plus 1 over 2s. Now taking LCM, so 2s will cancel out with 2s, and we will get the simplified form of the transfer function, which is equal to 4s plus 1 divided by 2s square plus 12s plus 1. Here is another example to further explain the concept of the transfer function. For the S-domain circuit in figure shown below, which is figure 16.19 in the book, find A, the transfer function, which is Hs equal to V0 divided by Vn. B, the impulse response h of t, the response when the input voltage is u of t volts, the response when the input voltage is equal to 8 cos of 2t volts. So we will solve it, part A. Part A can be solved by applying the voltage division rule, because part A we have to find the voltage transfer function V0 divided by Vn. So V0 should be found first. Now V0 can be found by from the circuit by voltage division rule. So V0 is equal to 1, which is the ohm. 1 ohm is the resistance across which V0 is measured. 1 divided by the total impedance of the loop. Okay. So basically VAB is the voltage across the terminal AB, and this voltage is divided between the inductor of reactance S and the resistance of 1 ohm. So this VAB is divided equally between the two components. Now, so V naught is equal to 1 over S plus 1 into VAB. Now, we have to find VAB in order to find V naught, because and VAB can also be found by the voltage division rule. So VAB is equal to the input voltage. Input voltage is equally divided between the 1 ohm resistance, and the other resistance will be the parallel combination of this branch resistance of 1 ohm, and this branch resistance is in parallel with the S plus 1, that is this branch total resistance, inductor and resistance, which makes this branch resistance S plus 1. So VAB is the voltage which is equal to 1 in parallel with S plus 1 multiplied by V naught Vn and divided by 1 plus that parallel combination, 1 parallel with S plus 1. Now if we apply the property of resistors, when resistor and inductors are connected in parallel, and then simplify it, so we will get VAB is equal to S plus 1 divided by S plus 2 divided by 1 plus S plus 1 divided by S plus 2 into Vn. Now VAB can be written as VAB is equal to S plus 1 divided by 2S plus 3. If we take LCM of both sides, that is the numerator and denominator, so S plus 2 will cancel out with each other, and the simplified equation will be the 16.92 equation. Now we can substitute equation 16.92 into equation number 16.91, and then we will get V naught. So V naught is equal to Vn divided by 2S plus 3, because S plus 1 will cancel out with S plus 1 here. So once we have found this, now we can apply the inverse Laplace transform. We will get the transfer function h of s, and then we will apply the inverse Laplace transform later on. So the transfer function, which is the ratio of V naught to Vn, is equal to 1 over 2s plus 3. Now we can also write part B. In part B, you see inverse Laplace transform should be applied in order to get the impulse response h of t. So h of s can be written as 1 over 2 divided by multiplied by 1 over s plus 3 over 2. Actually, we have taken 2 common from the denominator. So now it is easily you can apply the properties of the inverse Laplace transform in order to convert it into the time domain. So h of t by taking inverse Laplace transform will be equal to 1 over 2 e raised to the power minus 3 by 2t ut. E raised to the power minus 3 by 2t is the inverse Laplace of 1 over s plus 3 by 2. Now the last part, second last part. When the input voltage is equal to the step function u of t, then you see you can transform it into S domain, because the Laplace transform of the step function u of t is equal to 1 over s, and you can write V naught of s output voltage, which is equal to the product of the transfer function and the input voltage. Now the input voltage in this case is equal to 1 over s in S domain. So h of s is already given here, which is equal to 1 over 2 s plus 3 by 2. Okay, and you multiply it with the 1 over s, right? So we get V naught is equal to 1 over 2s into s plus 3 by 2. Now here we see it is in the denominator we have two terms, s into s plus 3 by 2. So we can use the partial fraction method to decompose into simple terms, so that inverse Laplace transform can be applied. Where A is equal to S times V naught S, and S is equal to, putting S is equal to 0, so we get A is equal to 1 over 3, and similarly we can get B is equal to minus 1 over 3. Now putting the values of A and B in the equation of V naught S, okay, so V naught S is equal to 1 over 3, you can take 1 over 3 common, so 1 over S minus 1 over S plus 3 by 2. Now apply the inverse Laplace transform method, so V naught T is equal to 1 over 3, 1 over S has inverse Laplace transform ut, and 1 over S plus 3 by 2 will have e raised to power minus 3 by 2 t into ut, so we can take ut common, so 1 over 3, 1 minus e raised to power minus 3 by 2t into ut is the inverse Laplace transform of the output voltage when the input voltage was a step function, equal to ut. The final part of the problem is when the input voltage is a cosine function at times cos of 2t, then we have to find the output voltage. So first of all, because we are using the concept of the transfer function to make the problem easy for us. So the input voltage in the S domain will be, we take the Laplace transform of 8 cos of 2t, so it will be 8 into S divided by S square plus 4. It is the S divided by S square plus 4 is the Laplace transform of cos of 2t, because omega in this case is 2, cos omega t, and omega is 2. So S divided by S square plus omega square, so 2 square will be give you 4. And so we can find the output voltage in S domain, just multiply the input voltage by the transfer function. So multiplying the input voltage by the transfer function, and the transfer function is already given in part B. So putting the values, multiplying both, we get 4s divided by s plus 3 by 2 into s square plus 4. Now this can be solved by using the partial fraction. So a divided by s plus 3 by 2, and then we have repeated roots s square plus 4. So that can be written as bs plus c divided by s square plus 4. That is the method of partial fraction. So next is we have to find a, b, and c. So let us do that. A can be found by multiplying v naught s by s plus 3 by 2, and then putting s is equal to minus 3 by 2. Applying the limit, we get a is equal to minus 24 divided by 25. To get b and c, we multiply the equation in the previous slide 16.93 by s plus 3 by 2 into s square plus 4. So the equation will be simplified as 4s is equal to a times s square plus 4 plus b times the term in the bracket plus c times s plus 3 by 2. Now further you can see we can compare on both sides the constant, the coefficients of the s and the s square terms. So constant on both sides, on the left hand side is 0, and 0 will be equal to 4a plus 3 by 2c, which will give us c is equal to minus 8 by 3a. Similarly, if we compare the coefficient of s, so on the left hand side the coefficient of s is 4, on the right hand side the coefficient of s is 3 by 2b plus c. It will give us b and c if solved in combination with the other equations. Similarly, comparing the coefficient of s square, so the coefficient of s square on the left hand side is 0, and on the right hand side it is a plus b, which will give us b is equal to minus a. Solving these three equations, the one for the constant, the other for s and s square, simultaneous solution of the three equations will give us a is equal to minus 24 by 25. Okay. Similarly, B will be equal to 24 by 25, C will be equal to 64 by 25. Hence, for the input voltage of 8 cos of 2t, the same voltage in the S domain will be equal to just putting the values of A, B, C in equation 16.93. So it will give us this equation for V naught. Now, it can be decomposed into time domain factors by taking the inverse Laplace transform. So minus 24 by इसका आ जाएगा e raised to power minus 3 by 2t, and the second term will give you cos of 2t, and the last term will give you some constant multiplied by sine of 2t. Just the table properties of the inverse Laplace transform are applied here, and we have this voltage now in the time domain. Thank you very much. If there are any questions, and they will be discussed in the class, and after this we will switch to the phasors analysis, the sinusoids and the phasors.